This is a brief video lesson on horizontal projectiles, the first video lesson of Unit 3, which is two-dimensional motion. A couple of key points about projectiles before we do an example. The first thing is that the x and y motion of a projectile are independent of one another. In other words, how the object moves horizontally does not impact how it moves vertically. And in the second bullet point, what I put here is that the horizontal velocity has no impact on the falling time. So whether you have an object that is projected outward at 2 meters per second from a certain height, or an object that's projected outwards at 200 meters per second, they're both going to fall to the ground in the same amount of time, assuming that they fall from the same height. When you change the height, then you change everything. But just because one is moving faster than the other in the x direction doesn't mean that gravity is going to pull it any differently down towards the ground. In the x direction, when we look at projectiles, we say that they have constant velocity, or their acceleration is zero, and this is assuming no air resistance. If there is air resistance, then the x motion, the velocity will decrease gradually. But we are going to neglect air resistance because it's our first time learning this, and we are going to say that the object has a constant velocity. In the y direction, the object accelerates due to gravity, and we use our kinematic equations and the acceleration due to gravity of 9.8 meters per second squared to do our calculations. To do an example of a horizontal projectile, what I want to do is set up a scenario where we have maybe a cliff and some water. It's pretty bad water. Let's get some better water. Get some water below, fish in the water, and we're going to put a cannon on the cliff. Here's the cannon. And the cannon is going to shoot a ball out horizontally, parallel to the water, and it's going to fall into the water, and we want to find the range or the maximum distance that it goes. Now, a couple bits of information. First is that the horizontal velocity of the cannon ball will be 60 meters per second, and we're going to say that it is 25 meters above its landing point. So what is the range? Well, the objective is to find the range. And this is a horizontal projectile because there is no initial angle here. It's just coming out at an angle of 0 or level to the ground. To do a problem like this, the first thing I recommend is setting up your information. And I do that by using a chart where I chart x and y motion, the givens. And in the y column, we also want to get into the habit of writing up and down. Very similar to what we did in Unit 2. For this particular problem, there is no up portion, so we can just cancel that out. And then I'm going to go through the information and write some things down. For instance, the initial x velocity is 60 meters per second. As we stated in the previous slide, the acceleration is 0 meters per second squared. This is in the x direction. There's no increase or decrease in the velocity. Let's see, we don't know the time that it takes to travel that distance, and we don't know the distance that it travels. If we think about down, the object doesn't actually start moving down until it's fired, so it's actually starting at 0 meters per second. It has no initial downward velocity. The final velocity is unknown. How fast is it moving vertically downward when it gets to the water? We do not know that. We do know its acceleration rate, because now in the vertical direction, gravity is accelerating the object, accelerating at 9.8 meters per second squared. The distance that it falls, we do know that, it's 25 meters, and the time is unknown. When you're doing a problem like this, we separate x and y, but the one thing that joins the two is time. Time can connect both sides. So our first goal is to find the time that it takes for the object to go down. The time down can be found if we look at what we have. We have vi, a, d, and t. We can use our equation. D equals vit plus 1/2 a t squared. And because the initial velocity in the downward direction is 0, this whole term essentially cancels. And when I isolate the variable t, I get t equals the square root of 2d over a. I plug in the numbers. 2 times 25 over 9.8. And get out my calculator. So let's see, 2 times 25 divided by 9.8. Square root that. I get 2.26 seconds if I'm doing a little bit of rounding. 2.25 each step. We'll call it 2.26. And once I have that time, that actually can transfer over to my x time as well, because the time it takes to fall is the time it takes to travel the x distance. So now, what we can do is find what we call the range. And to find the range, we can use the equation d equals vit plus 1/2 at squared again. Now this time, there is no acceleration in the x direction. So the term 1/2 at squared cancels out, and I'm left with d equals vi times t. And the velocity in the x direction is simply 60. And we multiply that by 2.26. And let's see what we get. I get 135.5. I got 526, but we'll call it 5.3 meters. And that's how we find the range. So the key thing when you're finding the range is that time value. And if you can do that, you can keep the x and the y motion separate, you're going to have success doing projectiles.